Our next speaker is Dr. Arthur Garcia, that is the lead of quantum computing at that is recognized quantum computing researcher at Barcelona Supercomputing Center. Thank you, Arthur. Sorry. And I leave you the floor. Thank you, Pioneer. I can't hear you. Is there a problem with your mic? Because I see you unmuted. Huh. Okay, let's wait a couple of minutes. We hope that this problem will. Now I see Arthur unmuted, but I can't hear. I can't hear you. You have not another microphone, something else?
Maybe we can arrange a connection by telephone. You can call the dial-in number.
Or by telephone, or yes, maybe.
Yeah, if the microphone is not working, you may call the number, and Daniele will enable you.
We can try. I have another user logging in with my laptop.
Can you hear me now?
Yes, now
okay.
We can. Fantastic.
I switched computer actually, so that's the easiest way to solve problems.
Well,
okay, now
a very good
let me
way.
try to share my screen. Sorry.
Very good. Perfect.
Okay. Finally.
Thank you, Arthur.
Okay.
The floor is yours.
Thank you. Thanks a lot. So I'm Arthur Garcia from the Barcelona Supercomputing Center. And I'll be discussing mostly about this ROSNet code, this library for quantum simulation on a supercomputer. But I'd like to use it as an excuse to discuss mostly the general topic of the relation between a supercomputing center and quantum computing. And this is, I think it's an interesting topic because, and it has been mentioned before that actually supercomputing centers have been in charge of justifying why do we need more powerful computers and which application need these actually new supercomputers in the exascale, for instance. And I see that it's a very similar problem to finding applications for these emerging quantum devices. So actually, it's the starting point of our research, where we were discussing, okay, we may not have like a really powerful quantum computers today. They are noisy. They are of not like a small size, but still there's a lot of interaction that may be interesting. And our solution to this interaction has been developing our own library for simulating quantum circuits, which is this ROSNet code that has some particularities. I will be not discussing in detail. We can discuss it later. But the general topic will be how to approximate the difficult problem of simulating a quantum circuit. Okay, so first a small introduction about the techniques we will be using, and also these underlying problems. And the idea here is that the Hilbert space where quantum states are living is huge. It's exponentially large. So that means that we have to keep some exponentially large information related to the size of the problem that we want to simulate. And this is something that if we want to fully exploit quantum properties of a quantum circuit or for a quantum device, we have to take charge of, and that's a big problem because there is no shortcut to this fundamental representation of quantum mechanics. So the idea is that, okay, then why do we develop quantum simulators if they have some kind of limited lifetime? And once we get around 50 or 60 qubits, most of these simulations will no longer be possible even with exascale devices. And the idea is that actually we can compare simulations with the results of real quantum devices And this is actually like really helpful because we have fundamental limitations to accessing the information on a quantum device because of the measurement problem in quantum mechanics. So we gain a lot of insight of what happens in a real quantum processor, and I think that's also very interesting by itself. But also we can test new algorithms before we have like proper devices, reliable and with really huge depth of these quantum circuits that I'm depicting here. We can test these algorithms beforehand, and actually using these simulations, we have discovered that some proposals for algorithms, once we stress this simulation to large sizes, start having problems that we couldn't see on small simulators of the order of 10 to 20 qubits. And then also what I mentioned here by optimal strategies, I mean mostly addressing the problem of quantum control. So we may have this device that we simulate on the supercomputer, and then we can simulate some quantum noise as well. And then we can devise some auxiliary agent or system that will be controlling and trying to reduce this quantum noise. And this can be simulated in this paradigm of a dual simulator and also a control system. So the underlying technique that we are going to present for our simulator is the tensor network picture. And the idea is that there is a close connection between tensor networks, which is a mathematical technology in order to simulate or operate over objects that are tensors, which are somehow similar to matrices. And so the idea is that we transform quantum circuits as tensor networks, which is very convenient once we think that these simulations will be run on a supercomputer because they can be easily parallelized. So instead of addressing the full state vector of representing the computation, we will be actually dealing with these small tensors at the beginning, representing the state and the gates. And then afterwards, we will be combining these tensors in order to obtain the outcome of this quantum circuit. Whenever we go to the exact simulation of the quantum state, we see that actually there is an exponential growth on the memory that we need, which is also the case in the exact representation of tensor networks in the worst case, but with some interesting differences. For instance, we have to combine the size of the tensor of the circuit, both in the number of qubits and also the depth of the circuit. So sometimes we are able with tensor networks to simulate larger circuits in the number of qubits, but with less depth or shorter depth of the circuit, which for some applications may be interesting. Especially when I was mentioning simulating real devices, these normally happen with a reduced number of gates, but may have a lot of qubits. So that's a particular application that may be interesting. And then the good thing is that we can perform some approximative techniques into these tensor networks representations in order to provide approximate solutions or approximate simulations. And we actually control the accuracy of these approximations, meaning that actually we can go to even larger systems as long as we relax the need to be very precise in the outcome. And there is an underlying physical motivation for that, which is interesting to discuss with physicists, which is as long as the state that represents this computation has not a large amount of entanglement among different parties, then this tensor network approximation is feasible and it's quite good actually. And these techniques have been extensively used in other fields of quantum simulation, especially with low dimensional systems at low temperatures. So I will not go into details, but basically there is a very handy graphical representation of tensor networks based on these small circles that represent tensors of different indices that we depict as some kind of outgoing lines of each tensor. And we combine these tensors by joining these lines, which means they have some common index, which basically you can refer to like vector matrix product, for instance, and then you have some vector which has only one index and a matrix tensor which has two indices. And then whenever you combine them together, is similar to performing some matrix vector operation, some matrix vector product. And then the outcome is a single vector, which is depicted like this. Okay. So this is the basic representation that is very handy in order to understand also the topology of this tensor network, which will be very important in order to assess how difficult some computations are. So the first step is just take the quantum circuit and then move to this tensor network representation. And that's a very trivial step. So there is no overhead in computation here. So that's something that happens actually in a natural way, because we can represent always these gates as matrices. Okay. So there is total equivalence among these two problems. And whenever we want to compute the outcome of the measurements of this quantum circuit, then we have to see what happens when we operate over this full tensor network, and whenever we perform some contraction. So basically, the idea is that we transform this quantum circuit, I'm picking here the Sycamore circuit, into this complex tensor network, and then we will optimize the contraction path. And this is interesting. It's not the same to start contracting this tensor network and operating tensors among them in different regions, because intermediate representations can be large. And this is the major limitation of this approximation to the simulation problem. So we have to be very careful selecting this contraction path, and that's a very hard problem. So there is no free lunch here. I mean, we have to solve that problem in advance before starting even to contract the tensors by themselves. But this can be done actually exploiting parallel resources. So that's interesting from the point of view of a supercomputer. Always trying to minimize this intermediate representation. And then once we know this contraction path, then we perform the actual contraction of this tensor network, and then we can sample over a reduced subset of tensors at the end in order to obtain the outcome of this quantum circuit. So I'm summing up this part. Basically, there are some techniques that actually we need to develop in order to be able to store these tensors in memory of a multi-node system, because sometimes these tensors, these intermediate representations, will grow very large before getting the final set of tensors as the answer. And then we have to use some different techniques in order to be able to manage these tensors that will not fit into a single node. So I have to say that this approach has been exploited by different groups. So it's not that we are bringing this for the first time into the simulation of quantum circuits, but our approach is based on a particular parallelization technique based on tasks, which we think is very interesting, in a way to bring all these resources to a general set of users or developers that probably are not that interested in the internal workings of all these tensor network manipulations, but they are interested in running simulations in HPC systems. So basically, the methods that we are addressing, this family of techniques in order to manipulate the tensors, are, I'll give you an example just to be really explicit. And what we call slicing is basically, once we have set up some given tensor network, then we can eliminate some of the links of this tensor network, which is equivalent as reducing the memory requirements to represent and operate this tensor network. But as a trade-off, we need to perform this contraction or this operation over the tensor network in parallel with some time overhead. But the good thing is that this is totally parallel, so we actually forget about this link, and then we perform this reduced contraction many times, and then this can be done in parallel, and at the end we can just combine the results. So this is like a general approach that may allow you to reduce the cardinality of these tensors and thus reducing the memory requirements. So basically the picture will be, okay, we have these two tensors that we want to contract, meaning that the outcome should be a single tensor combining all the indices. And then we just remove this link, making this like a common index that is not explicitly represented in the tensor network. But as a trade-off, what we have to do is to operate these in parallel. All the possible combinations of these two tensors that will be equal to the operation represented before by this link disappears, and then we operate over these tensors. Okay. And the basic idea is that then we can have tensors that are arbitrarily large, and the only thing we have to do is to split them in blocks, and then all the operations related to the big tensors are actually done in these reduced tensors or these reduced blocks. And you can see, for instance, here we are contracting two tensors, and this should be the outcome. And then for each contribution on the outcome, there is a lot of like different combinations of these blocks that have to be done separately and can be done independently. That's the interesting thing, to be done in a supercomputer. And then once we have all these blocks together, then the operations on the subblock level are combined together in order to bring each of the components of the final tensor. That can be also represented in a multi-node way. So that's also interesting. There is no requirement to have everything sitting on the same node. How do we do that? I mean, there are many different approaches. All these different blocks can be done, can be constructed sequentially, which has a lot of time overhead, but it's very efficient in terms of memory. There is some structure as a tree that may be very convenient if all these, if there is a lot of work to be done at the beginning, when there is a major level of parallelization. But actually, in many situations, the big cost of the construction of the full tensor network happens at the end, when there is no a lot of parallelization. So it's not surprising to see that actually this approach is not very efficient. What we discovered is that actually something called commutative reduction is very efficient. And I don't have to be very precise here, but the idea is that this approach has some benefits. In particular, we can compute each of these contractions in parallel, but the common composition of all these solutions will happen sequentially. Okay. So the idea is that we have this trade-off between how small these blocks have to be and bring in more parallelism, and also the overhead that we will have both splitting and joining these blocks computation. So there is some kind of middle spot where we know this approach will be very, very efficient. And also, actually, beyond this heuristic, there is another thing which might be interesting, that these block sizes can be related to some particular architecture that we will be using in order to perform this actual construction of the tensors. Meaning that, for instance, if we have a lot of GPUs, we can just optimize this spot to be so that each of the block operations will fit into this GPU memory, just like boosting a lot then the algebraic operations. Okay, so we program these over a library called PyComs that will take care of most of the parallelization demands of this approach. And basically, it's task-based, and it will distribute all these tasks in different nodes by itself. So the idea is that we are going to develop the code just with a sort of decorator that will tell when when there is a dependence on data as input and output of each of these functions. And then these PyComs will take charge of the full dependency graph of all these tasks in terms of data, and also the parallelization will happen inside the runtime of PyComs, which is very convenient. Also because these PyComs has been developed mostly at the Barcelona Supercomputing Center. So actually next door we have the people developing this library, and this interaction has been very interesting for us while doing this ROSNet code. So just to finish, I'd like to show you some of the results that we have done for very large circuits, actually. So somehow, naturally, in the community, the Sycamore circuit has become some kind of objective or very useful benchmark in order to try libraries. And we start checking our code with 53 qubits simulation of the Sycamore, and the combined depth is of 12 levels or 16 levels. Let's say that the Google experiment is down to 20 levels, and there are simulations also using similar techniques at that level, but that will require the largest supercomputers in the world today. And what we have been doing is mostly a scaling analysis of this approach in our system in Mare Nostrum 4, down to a few number of nodes. But already we were able to simulate the Sycamore circuit down to quite a significant depth. And overall, the main interest was to check if these both sequential or commutative approaches were interesting and feasible with the memory requirements that we had for a particular given number of nodes. So using trace analysis, and this is also a nice feature of using PyComs, we have access to all this information of what is going on in the full supercomputers. We actually know that our current version of the ROSNet code is already let's say, efficiently distributing all this load into different nodes, into all the available nodes. And also the runtime that may be under stress in some situations, as you can see here, is actually can manage to distribute all these tasks and also to perform the actual constructions of the system. Where is all the computation time going? So basically, it's this tensor.operation. So we basically are all the time constructing tensors, which is very similar to multiplying matrices. And these matrices can, in the worst case, grow exponentially large with the system size. So there is this fundamental limitation of the quantum simulation is already here in these operations, in this tensor dot. But nicely, we can see that actually there is some overhead, significant overhead, but not a lot of overhead on the way we manipulate the data using this PyComs library, basically converting the serializing and deserializing the objects into the disk space where we store all the information. So there is this is to complete this picture. We have to write and move data among different nodes, and that will take a lot of time. But it's done transparently for the user using these PyComs, and also it may happen while other nodes are actually performing contractions. And just some weak scalability analysis for given number of nodes and different increasing sizes of these matrix or these tensors objects, we actually see a nice efficiency along growing system sizes. You can see some drop in the performance here, but this actual point we've been studying it, and we know that the major problems were the bottleneck was actually on the runtime of this PyComs library, and that has already been solved, meaning that actually having this interaction with people developing the underlying libraries is also very interesting. What is not very clear here is that actually by using the commutative approach, while it may be slightly slower than the sequential, allows us to reach to larger experiments with the same amount of memory, which is interesting. There is some overhead by the sequential approach that doesn't have the commutative, allowing us to reach a larger system. And well, this is a very similar analysis, just changing the block sizes and for different number of nodes. Okay, so let me just jump to the conclusions. And the first part, I try to justify that actually it's very interesting to have a tensor network-based code on supercomputing centers in order to approximate or simulate quantum circuits. And while there is a lot of work being done on this optimal contraction ordering or suboptimal with using heuristics, this is already a hard problem, and it's very interesting by itself. But I've been addressing mostly the second part of the problem, which is once having this contraction ordering, how do we perform the contraction manipulating these tensors that can be really, really huge? And our solution for that is using this library we have developed at this supercomputing center in Barcelona, which is called ROSNet, and basically it's an out-of-core data allocation based using this PyComs runtime. Allows us for having like tracing and profiling, and that has been very, very useful in the development and first experiments that we run on multi-node systems, and also the potential for using heterogeneous architectures, meaning that these final contractions can be performed in GPUs or different architectures actually. And the basic tool and in order to manipulate these tensors, these very large tensors, and going beyond the limitation of a single node, is using these tensor slicing techniques that minimize the memory usage. So thank you for your attention, and I'm open for questions.
Thank you, Arthur. Very interesting. Your emulator seems really interesting, and also the fact that I want to tell you that the fact that your strategy to parallelize the tensor slicing strategy is very, very clever. My congratulations. And is there any question for Arthur? If not, I have a question, and I think that okay, I can say it. And you used ROSNet also for some simulation, okay? But I did not understand, maybe I missed it, but I don't know. Did not understand how many qubits did you manage to emulate with ROSNet, with some try that you did. That was I missing this information, or?
I mentioned for this particular experiment that we were showing that we were on the same setting as the Google experiment. So these are 53 qubits.
53, okay.
Yeah, but I
with what level of approximation? Because what amount of RAM did you use for emulate 53 qubits with the tensor network method?
So the point here is with tensor networks is actually the important thing is the combination of both the number of qubits and the depth of the circuit.
Yes.
Because if I have a very trivial circuit, I can simulate hundreds of qubits. Okay, and that's interesting for some situations. For instance, if you want to simulate low depth circuits. In our particular case, we were, let's say, halfway the full sycamore circuit of the supremacy experiment. So this is called number of cycles. The full experiment of Google was 20 cycles, which involved different quantum gates among neighbors. And in our case, we were between 12 and 16. But it was an exact simulation. So we were not assuming up to any truncation or any approximation. So the interesting thing, let me say, about these tensor network methods is that actually you have some level of tuning all these properties of your simulation, which may be very handy for different scenarios.
Very remarkable. Congratulations. Okay, and so okay, and so you said that you made an exact simulation for this experiment, but just to say, if you make some approximation, how much qubits that you can added qubits you can emulate for the same circuit?
That depends a lot on the properties of the quantum gates. And the hand-waving argument is that if these gates are really entangling gates or create a large amount of entanglement between any partition of the system, then my intermediate tensors are going to be very, very large.
Okay.
While if I have very slightly entangling gates, and the amount of entanglement along all this simulation is reduced, then I can perform a lot of truncations of these tensors while having still a very good approximation. So there is this trade-off, which is very difficult to quantify, but I can actually run different simulations with different cutting numbers and see if they are consistent. So there is a way of proving that actually your results are consistent.
Very interesting. So we have not only the state vector emulator, but we have also other techniques, HPC techniques to emulate quantum computers in a very efficient way. Okay. Yes, if there is no other question, I think that we can thank Artur. Thank you so much for your very interesting talk.